We'll wait for 5 minutes. We'll start at 6:05. The screen is visible to everyone. So I think we can start. Okay. So good evening to everyone. Uh, Myself Swapnil Balasaheb Godke. Currently, I'm pursuing my PhD at the Indian Institute of Technology, Turkey, and I will be handling this session. So under the guidance of Professor Sudhir Mishra sir. So who is the instructor for the this course, Development and Applications of Special Concrete. So in the last lecture, I think someone has asked me why in the ITZ why CH percentage is higher than the CSH, although cement percentage is less, right? Yeah. So is there anyone able to find out answer for that one? Has anyone tried? Okay. So what happens? Uh, there is a we called wall effect. So because of the coarse aggregate inclusion surrounding the coarse aggregate, we already observed that or studied that like water due to the bleeding, water percentage will be the higher surrounding the aggregate. So that due to that coarse aggregate wall effect, cement will not able to dense in that area, and due to the bleeding effect also, cement will be the settle down. So whatever the less amount of cement available, that will not able to create the large amount of the cement consumption, so large amount of the CSS formation. So what happens? CH requires more space to create the hexagonal plate-like form. In the presence of CSH, CH will not get that much space. But in the case of the ITZ, CH have plenty of space because of the less cement grain particles, and because of and the where that CH comes from, that CH comes from the ionic solution, that calcium ions Ca2 plus migrate toward the water rich zone from the bottom of the or the matrix of the cement towards the ITZ. So that Ca2 plus acts with the water and create the calcium hydroxide in the that ITZ area, that is a weaken area surrounding the coarse aggregates, and that orientation of that one is like perpendicular to the aggregate. You can see this type of hexagonal structures are highly a high percentage is available compared to the CH. And CSH, one more thing is that the high local water cement ratio means CSH that does not form sparse or dense. So it will be the fluffy. So low density CSH will form, and then to the bulk matrix. And main thing is that competition. So because of the rapidly forming CH and yttringite, that is CSH, like needle-like structures will form, consume available space, and that's why the formation of CSH, whatever the space required, it is very less. So that's why, because CH will react very fast compared to the CSH formation, and CSH formation, CH and CSH. So that's why percentage of CH and CSH is very high into the ITZ region. Understood? Yeah. So that's why we have to be always remember that whatever the thickness of the ITZ, usually it will be the 50 micrometer. So in that region, CH and CSH percentage will be the higher. It is the weakest part of the concrete structure or weakest zone, and higher porosity, higher water cement ratio. These are the main points you have to be remember. Okay. Yeah. And these are the references. If anyone wants to read further, there are plenty of research papers available on the ITZ, because this is the more important topic towards the concrete strength and that all things. In case of the high strength concrete, it will not follow crack path surrounding the aggregate. It will follow the crack path within the aggregate itself. So why ITZ is strong in that part, that is also research available. Plenty of research papers available. So you can read this also. Okay. So I hope you have completed the first week assignment also, and you have started the second week. lectures. I think third week lectures also has been released, right? Yeah, yeah. So in the first week, we studied that what are the constituents of the concrete, what are the fresh properties required, what are the hardened properties required, how we'll find out the workability with the different types of the test, and why hardened properties differ in the series, series and parallel, two different types, but actual concrete, it will in between that one, behavior of the concrete in between the series and in between the parallel, it will not actually the series, it will not actually the parallel condition. And itz is the one of the major part we have saw. In the second week of the lectures, there is the fundamentals of proportioning of concrete mix. Proportioning means proportioning means what? Anyone can tell me? According to Indian standard codes, we used to design the mix, right? So designing the mix, concrete mix, will get the proportion of the everything like sand, cement, fly ash, and silica fume. Or if you are using silica fume or any supplementary cementation material like that. So that proportioning, it should we can't take any arbitrary proportion and we can prepare the concrete mix. We have to design the mix, right? According to the code, we have to design the mix. We have to find out the proper proportions, and then we have to try that proportions in the lab, and we have to find out whether it is following the workability parameters or whether it is following the strength parameters after the 28 days. If they are following some environmental conditions, also we have to take and care with respect to the durability aspect, such as IS 456 suggests that you should not go for the 400 kg per meter cube of cement, more than that one. Such parameters we have to be considered while designing the concrete mix, and that is exactly called as fundamentals of proportion concrete mix. Understood, right? Yeah. So one major thing in the workability we have studied in the last lecture, that is slump. Slump. So slump means we have to find out the workability of the concrete. That is the one of the test, slump test. And for that purpose, Abraham cone we are using. And in the three layers, we will place the concrete. In that one, we'll give the tamping on the each layer with respect to the tamping rod. We'll lift the Abraham cone and we'll see how much slump we are getting. And based on that one, we'll find out the workability of our mix. But this slump, on what parameter it is dependent on? Basically, slump is mainly dependent on the unit water content, which is in kilogram per meter cube. So if you see these lines A to B, C to D, E to F, what it indicates? It indicates that as the unit water content goes on increasing, the slump value also goes on increasing. This is a like simple observation. What we say, if we increase the water content, flow will be more, right? Workability will be more, and because of that one, we'll get the higher slump value. If the water content is less, we'll get the lower slump value, more stiff concrete. We have to go with the different tests, like is test, VB time test. We saw that one, right? But thing is that we have to be remember why this line is not from the origin, because this linear line will follow only certain range. So how to find out that one for particular your concrete mix? Depend upon the your constituents of the mix, your water content. You have to find out this line, and then this slump is dependent on the unit water content. So you have to remember these things. Slump is dependent on the unit water content. Okay. Then one more thing we saw last time, that characteristic strength. So characteristic strength, we saw 30 samples we tested, we got the normal distribution plot, and we find out the two parameters. What are the two parameters from that normal distribution? We'll get it: target strength and characteristic strength, and we'll get the standard deviation for particular individual strengths. Like so, if you see this normal distribution plots A, B, and C, and these are the compressive strength on the x-axis. This is the mean M1 and mean M2. So can anyone please tell me, what is the difference between A and B you will observe? Whether these two plots are exhibiting same characteristics, same target mean strength and same standard deviation or not? Same target mean strength. I'm asking about A and B, right? Will it exhibit same target mean strength or different? Any other? FCK is different. See, what is the target mean strength? This is the peak value, right? This is yeah, target mean strength. This is, and standard deviation, will it differ or same? Yeah, that will differ. What about A and C? Standard deviation will be the same. Actually, two plots, but mean strength is differ. Why? Here it's M1 and here is M2. Mean strength are different. It will be visible as well. So what it indicates, mean strength is higher. M2 means what is indicating? Water cement ratio may be less as compared to the this mix. Because of that one only, it's showing higher strength, right? Because strength is mainly dependent on the water cement ratio. We already saw in the last lecture also. And slump, here we are saying slump is dependent on the unit water content. So what actually mean strength represents? The average strength of the concrete, and is directly influenced by the quality of the materials used and the proportioning of its constituents. Understood? Mean strength is the mainly the indicating the quality of the materials used and the proportioning of their constituents. And what are the standard deviation? It indicates the individual strength deviation. We tested 30 number of samples of the cubes. We are getting some of the deviations of that one, some difference between the strength values. So based on that one, we'll calculate the standard deviation. Okay. So if the spread is more, it's good, or spread is less is good. This spread, if you compare A and B, which one will be the good mix? Which one? Spread A will be good because we have the less standard deviation, means more nearby results we are getting, right? Yeah. So we have to remember these things like mean strength and standard deviations. So this will be the parameters we'll get the value to calculate the design mix. While calculating design mix, we have to be understand these parameters. So we already saw strength and water cement ratio has a direct relation. As water cement ratio goes on increasing, strength goes on decreasing. So strength goes on decreasing. Similarly, here also A, B, C, D, E, F lines are there. These lines are dependent on the. Can anyone tell me these lines depend on the what parameters apart from the water? Properties of what? No. Cement and age of the cement and age of the testing. But in the earlier one, this one slump versus unit water content. This is depend on the aggregate shape, size, texture. That is slump content or slump value is dependent on the aggregate content. But in the case of the strength, it is dependent on the cement and the age of the strength. So we already saw this one also in the last lecture that water cement ratio calculations we use the target mean strength, and design of concrete mix we are using the target mean strength, quality control and acceptance criteria we are using the characteristic mean strength. I hope you remember these three important points. So anyone have any doubt about these two graphs? That's a slump and strength. It's not like the three. We can plot in number of also. It's just for the representation. Number of different how it's depend on the cement and age. Suppose you have cement here different, age of the concrete is different, here different. Like that we have plotted. We can plot more also. It's just a representation. Any other doubt? Yeah, yeah. Listen. Hmm. Right. Yeah. What? Even enough, there is enough water. Some amount of cement is okay. Still, 18 to 25% water is required to get the fully hydration. Yeah, but we are providing extra amount of water. If you saw normally, 0.35 to 0.45, almost zero point 0.5 also sometimes we are using the water cement ratio. Mm. Okay. So it's depend upon the hydration mechanism where the mechanism internally. Sometimes it's not like always it remains what we called unhydrated. Sometimes remain or sometimes not remain. It's depend on the hydration reaction inside the concrete. So that's why to do not evaporate extra water from that one. We are going for the curing also. So whatever the water available in that concrete or the cube will hydrate remaining unhydrated cement. Yes, sir. Yeah, yeah. I think they can open. diffusion. Yes. Yes, sir. Yes. Just 14, sir. Mm. This one? Mm. Yes. Mm. Yes, sir. Yes, yes, sir. Yeah. Of course, sir. ठीक है ना? Okay. Fine. Okay. Okay, sir. Thank you, sir. Yeah. Yeah. Yes, sir. Yes, sir. Okay. Thank you, sir. Okay. Thank you. So I think we are here, right? Yeah. So strength versus water cement ratio. So whatever the plots we got it. So the every point on the plot indicates the target mean strength. So what it indicates, every point on this line indicates the target mean strength. Then only it is the linear line we are getting on the strength versus the water cement ratio. So similar thing has also explained in the lecture as well. For given materials and their properties, the variation may be taken to be on single line for the given age, particular age. These are the for the different age and cement type. For the particular single age, then each point on this line represents the average of the normal distribution obtained when testing a given concrete. You see, this is the normal distribution, and the whatever the target mean strength is there, that is the one point. This is the point, or here different type of concrete, and that is the target mean strength of that point, that concrete. Similar, we join that point and we got this line, and based on this one we can get the relation between the water cement ratio and strength. So strength is the directly dependent on the water cement ratio. The next parameter is that sand to aggregate. So sand to aggregate, if you see, if the in the normal concrete it is around 32 to 45%, then if it is sand to aggregate ratio is very low, so what will happen means aggregate content is very high, right? So if the aggregate content is very high, what we call no fines concrete. And if sand to aggregate ratio is very high, then sand content will be high. So we called it as mortar. Means coarse aggregate content is less or maybe absent. So sand to aggregate ratio is also very important parameter while defining the or preparing the design mix. So this is the one like block in which coarse aggregates are put it to in the compact position. So if you see, there is some void present in between these aggregates, right? If you pour or if you fill that voids with the paste, cement paste or the mortar, can you please tell me anyone whether it will be workable if you only fill the voids? Yeah, right? Right. So the concept is that basically mortar film thickness or paste film thickness. Whenever we want to get the some of the workability, these voids should be filled with the paste or the mortar, and there is some amount of excess paste or the mortar should be there, which can create some amount of thickness surrounding the each aggregate. So which will decrease the contact between the direct contact between the aggregates. Why? Because of that thickness of the mortar or paste film thickness, and create the lubrication. Because of that enhancement the lubrication, the workability will be high. Now if the thickness of that mortar or the paste film thickness goes on increasing, the concrete will be go from the workable to the flowable. If it is less, the interaction between the coarse aggregate goes on increasing, and because of the friction the concrete will be very stiff or have the very high viscosity. So right, so we did not require only to fill the voids, we required some amount of extra paste content or extra mortar content. So okay, is there any doubt? Okay, so if you see yes, yes, please. Hmm. Yes, right, below it. Yes, Hmm. Right, right. Yeah. And only for the acceptance we are using the FCK. Suppose we are giving some like M20, M30. So whatever the M20 or 20 or 30 indicate, that is the characteristic strength. Okay. So see, this is the plot. This is the table. If you see, this is the W indicates water content, C cement content, water cement ratio, strength, and slump. Now we understood that water cement ratio influences the strength, water content influences the slump. So based on that one only, we'll understand this table. If you see, we have the water content 180 kg, cement content is 360 kg. So we are getting the water cement ratio 50, and strength we are have 35, and slump is 80. This is the reference mix. Suppose if we increase water content and we kept the same cement content, what will happen? Water cement ratio will get increase. So we observe that water cement ratio also increases and water content also increases. So because of that one, both the strength and slump will get differ. What happens? Because of the increasing water cement ratio, strength will get reduced as compared to the base mix. You can observe here it is 35 and here we are observing 30. Understood? Then if you are using water content, increasing water content, earlier it was 180, now it is 200, so we are getting influence slump also. So slump value also goes on increasing because of the increasing water content. Workability also goes on increasing. But if we kept same 200 kg water content and cement content, we increases 400 kg, so we'll get the only that earlier water cement ratio 50, that one. And because of the water cement ratio is same as earlier as the base mix, we get the same strength 35 because water cement ratio has not changed. And slump, why we are getting same slump? Because we have not made any changes with respect to the second mix in the water content 200. So because of with respect to that water content, whatever the slump is there, that whole value only we are getting here. So basically the main thing about this table is that how water content and water cement ratio affect the strength and slump value. Understood? Yeah. Okay. So these plots we already saw, slump versus unit water content and compressive strength versus water cement ratio. Just you have to remember these lines depend upon the age and type of cement in the case of the compressive strength and water cement ratio. And the slump and unit water content it's depend upon the aggregate properties such as shape, size, texture. These are the influencing parameters for increasing or decreasing the water content. So because of that one only slump value will get differ. So basically, what inputs required for the design of the mix? Air content. So air content may be given. If it is not given, what value we will take it? Usually in the design of the mix, we saw in the last lecture, 1 to 2%. Right. And if we are designing for the freeze thaw resistance, what will be the value? 4%. Up to 4% usually you will take it. Second, after the air content, we required slump unit water content relationship. This one. Then we required compressive strength water cement relationship. Then required sand by aggregate ratio, material properties such as specific gravity of cement, fine aggregate, and coarse aggregate. And other special requirements, maximum water cement ratio, minimum cement content based on the IS 456, which follows the durability aspects. Okay. Then, first of all, step one will go for the air content, then water content for required workability will calculate, cement content using required water cement ratio will calculate, then sand content within the total aggregate volume. Total aggregate volume contains sand plus coarse aggregate. And after that, we'll get the coarse aggregate. So, already this example has been solved in the lecture, but we'll just see how we have to solve this one. So, this example is given air content 5%. So 5% of 1000 liter. How much it is? 50 liter, right? So we got the one value that is air content is 50 liter. We have value of the slump, which is 80 mm. Characteristic strength is 25 MPa. So can anyone please tell me we have to design for 25 MPa or we have to make some calculations? Yeah, please. Yeah, target strength. So how can anyone calculate how much it will come? Because we have given the deviation also we have given. Yeah, how much? 3. Yeah. So it I think almost it will come 29.95, right? So means approximately 30 MPa we have to design the concrete. So we have the design strength is 30 MPa. Slump value we got the air content 50 liter. Then we have the sand to aggregate ratio, that is 0.36, and other material properties 3.10 cement, specific gravity, fine aggregate 2.61, and coarse aggregate 2.63. So we have the 30 MPa and the design strength. So based on that one, can we calculate? Suppose we consider slump value 80 mm is there. We consider slump value we are getting the water content 160 MPa. We suppose that we are getting 160 kilogram per meter cube water content for with respect to the slump 80 mm based on this plot, right? We have the slump value 80 mm suppose, and with respect to this one we are getting 160 kilogram per meter cube water content. So calculate the cement content, or we have the 30 MPa, 30 MPa design strength. So we get the water cement ratio suppose zero point 0.5. Can anyone calculate? We have the water cement ratio zero point 0.5 and water content 160. Can anyone calculate how much will be the cement? 320, right? So 320 convert it into liter, 103 divided by 3.1. Similarly, for what others we got it, we got the 50 liter of air content, then we got the uh, water content 160 convert to directly 160 liter, right? So 50, 160. Then we got the cement 103, right? 320 converted 103, right? Na? Yeah, 103.2. Then we have the sand to aggregate ratio 0.36. So how we'll calculate the other things? Total aggregate content, how much it will come? So mm, yeah, so how much it will come? 68168. So we have 50 liters air content. Then we have 103 point, how much? 3.22. So that is our cement content. Then we have other thing is water. We got it. Water is 160. Yeah, 160. So 6 at 6.8 sand to aggregate. So how will calculate the sand content from that one? Sand and aggregate content. Hmm? Yes, guys. Uh, right. So we'll get it from there, sand, and then we'll get the like one out of 1,000 remaining one. We'll get the coarse aggregate, right? Yeah. So this specific gravity values we use for conversion of the liter kg to liter or liter to kg purposes only. Further, concrete mix proportions, analysis and adjustment. So we design the mix. Suppose we design the mix. Now, suppose we just now we saw the example. We design for the 30 MPa, but we are not get the desired properties such as the we are not getting the proper workability, whatever we require. Suppose we require the 80 mm slump, but we are not getting. Suppose we are getting more 90 or less. Suppose, and whatever the strength we required, we are not getting desired strength. So that time we have to do some adjustment. And other time, suppose in the industry also, suppose we are using some type of sand, then we change the sand, fineness modulus changes drastically, or the any other binder properties also changes, binder batch also changes. We have to make the changes into the our design mix accordingly. So you see, this is the property target and actual. Slump value target is 8 centimeter, but we are actually getting 7. Air air is 5, and we are getting 4. Okay, so for that purpose, uh, from the lecture only I have took this table. That is the Japanese code is there. It has given some corrections in the sand to aggregate ratio and correction in water content. For zero point 0.1 increase in fineness modulus of sand, if fineness modulus we require to increase zero point 0.1, then correction in SA should be plus zero point 0.5 zero point 0.5, and correction in water, it's none. Yeah, this is the actually I have taken it from the lecture only. Sir has explained this is from the Japanese code only. Yeah, actually I have not seen in the Indian code this thing. Uh, Usually I have to ask sir about that one, but usually in the lab, whatever we'll do trial and error only. But in the industry, might be industry people can have some lights on that one, how they will tackle with this situation. Yeah. Okay, desired. So you will do it for the small batch basis in the lab itself. You are Hmm. Okay. Okay. So you will plot the normal distribution. Uh, okay. So basically, you are also using that trial and error approach only. Okay. But the Japanese code has given this table. So maybe in the Japan they are using this as the reference. So if now we in our case this one we have to get the target is 8, but we are getting 7 centimeter. So for 1 centimeter increasing slump, there is no correction required in sand to aggregate ratio, but we require the correction to add or increase the water content 1.2%, right? And for 1% increase in air content, correction in SA, sand to aggregate minus 0.5 to 1% is also required, and correction in water is also minus 3% required. So, can anyone tell me total correction how much it required for this? This actually this both the properties regarding to the same concrete mix. So for that concrete, yeah, no total, yeah, slump is concerned that is 1.2% in the water, but total I am seeing. So total both the corrections we have to together incorporate together in the mix. So how much is the net? Yeah, this is plus 1.2 and minus 3. So because air content also we have to do. So will come into minus 1.8, right? And here for slump, as by A is none. Here you can take minimum minus zero point 0.5 to 1. So if we consider 1% minus 1%, we have to or decrease the 1% of sand to aggregate ratio. So net we have to do for the that particular mix. Understood? Yeah. Okay. So another example is that here air is also given again 5%, water is 175 kilogram per meter cube, water cement ratio 50%, and coarse aggregate content is 48%. So just take 5 minutes and calculate how much quantities will come into the, if you can tell me in kg or in the liter also, the same specific gravities you can use earlier one, this one. For the cement 3.10, 2.61 and 2.63. Air content is 5%. So how much out of 1000 liter? 50 liter. Okay. So water is 175 kilogram per meter cube. So in the liter also it will come into, because specific gravity is 1, so 175 liter. We got the two values. Cement, water to cement ratio is 50%. So how much cement will come? 350 kilogram, right? Because we have water content, we have water to cement. So 350 kilogram, and converted into liter, we have 3.1 as the specific gravity. 96 point. No, 350 divided by 3.1 will come, na? 1. Yeah, 12.9 liter. So we got the air is 50 liter, water is 175 liter, cement is 112.90 liter. Now you can observe here they have not given any S by A ratio, but they have given coarse aggregate content is 48%. So what it indicates, 48% of 1000 liter means already get we got the value of the coarse aggregate content. How much it is? 480 liter. 480 liters. So remaining value out of 1000 will be the sand content. So how much it will be? 182.79. Okay. All are got same value. We have 50 liter air, water is 175, then cement is how much? 112.903. Then we got 480, this one. So minus 1000, 182.097. So understood? Sometimes they will give in the if it's in the exam also. Sometimes you will have the value of the S by A, so you can go with that one. Or sometimes you will get the directly value of the course aggregate percentage. So percentage is always because sir has cover all the lectures in the volumetric basis design only. So you will get out of 1000 liter only. You have to convert that 48% into 480 liter. Understood this example? Yeah. Yeah. Uh, no, I have not observed like that for the course aggregate, but for the cement content is there up to 400 kg. Yeah, 400 kg per meter cube. But usually 60 to 70% coarse aggregate will be in the concrete. But I have not observed any codal provisions like you could not go beyond that one like that, because basically you have to be careful about your durability perspectives. Like um, it should not or you should be weathering, and that all actions you have to be taken care. So freeze, for instance, if you are considering air content, how much we have to incorporate, so that criteria are there, like water cement ratio zero point 0.5 will be maximum or 0.45 will be maximum. That criteria is there, but I have not seen regarding to the course aggregate. So next is that concrete mix proportions. So another example is in this one. Normal concrete is proportional with the following conditions. Air content is 5%, unit water content 180 kg, water cement ratio 45%, and coarse aggregate content 40%. First of all, calculate now how we have calculated last one. Na? Similar, you can calculate all the mixes in the liter, mix constituents in the liter or in the kg also. Then we will see the next part of this example. So air content will be how much? 5%, 50 liter. Unit water content 180 kg means water also will come 180 liter. Hmm. So water cement ratio we have 45%. So calculate the cement content, how much it is? 1 to 9. Okay, by volume you are saying. And in the kg it is coming 400. Hmm. 1 to 9.03. Okay. Then we have coarse aggregate content. So 40% means how much? 400, 400 liters, right? So 400 liters. So we have air, water, cement, and coarse aggregate. So how much will be the fine aggregate then? 241, right? Everyone got it? Okay. So convert this thing into kg also. Air will be same. Air will not come. Then water will be 180 kg. Cement will be 400. Coarse aggregate 400 divided by 2.63. Sorry, 2.63, right? 105. Okay. Hmm. And what about fine aggregate? 6 to 9. Okay. So we got it, this one. Now you see, we got the cement, how much? 400 kg, right? Everyone got it? Everyone is there? Yeah. So see the next part of the example. What they said, other conditions dictate that cement content cannot exceed 320 kg. So we are not allowed to use cement content beyond 320 kg, but we are using in this mix 400 kg. So we have to use some or made some adjustment where we can reduce the cement content. So how we can reduce? There are two options they have given, or we also know we can use the water reducing admixture. That is a super plasticizer. So we can reduce the water content, and ultimately we can reduce the cement content. Similarly, we can replace cement content with any type of mineral admixture. So mineral admixtures, what are there? Fly ash, silica fume, then GGBS or rice husk ash, like that. And but their inclusion is mainly dependent on their efficiency. So efficiency they have given mineral admixture here is 75%. Okay. So first of all, we'll see whatever the water reducer that can be used to reduce the water demand by 20%. So if you reduce the water content 20%, 180 liter is there. So how much will be if you reduce 20% water of 180? How much it will be? 144 liter, right? Yeah. So 144 liter will be there, or 144 kg. Then made calculations according to that one. Cement content. Now you can calculate cement content. Water cement ratio you have 4.45. So how much will be cement content now will come? Or according to 1 foot 320, right? Yeah. And other things, air we have 50 liter or 50. Then coarse aggregate content we have to fix. That is 400. So 1052 in the kg, right? Convert all things into the liter and then see how much fine aggregate is coming. 50 liter is the air. So 144 liter is the water. Cement, how much in the liter? How much cement will come in the liter? 103.22. Okay. And coarse aggregate content is already 400 liter. So how much fine aggregate content now? 30 302.78. Now you can observe in the first that earlier whichever earlier base mix we have the 400 kg of cement, that is 129 liter suppose, and fine aggregate in that case we have 240 liter. Now fine aggregate content goes on increasing because we are keeping the constant coarse aggregate. Fine aggregate content increases from 240 to 302 to maintain the same mortar because we are reduce the cement content, right? So that's why mortar content to maintain the same, fine aggregate content goes on increasing. Understood this one? First one, 20% how we reduce and how much we got it, 320 kg. Yes. Now second one you can do mineral admixture with an efficiency of 75%. How we will do? We have 400 kg cement, right? We required 320 kg. So how much will be the difference? 80 kg is extra, right? So we have to replace that 80 kg cement with some of the mineral admixture. But mineral admixture already have 75% efficiency. So how much mineral admixture we have to add to replace the 80 kg cement? No. Suppose we added, for example, we added 100 kg mineral admixture. We are only replacing, right, 106.67 because efficiency is only 75%. That's why higher mineral admixture is required or a higher replacement quantity is required, right? Yeah. So you see here mineral admixture is 106.7. Coarse aggregate content is 1052. Same here 320 and here 180. So can anyone please tell me whether this paste content will be same or different? No, you can see these all are kg, right? You see here we have the paste content how much? 400 kg. Here we have 320 kg with reducing water content by chemical admixture. And now we are replacing mineral admixture, cement content by mineral admixture. So obviously you see 320 plus 106.7. It is more than 426, right? 426 kg cement plus mineral admixture. So paste content means powder content plus water, right? So paste content in this one is higher as compared to the base mix. So this is the very important observation. You can see because of the replacing the mineral admixture with cement by mineral admixture, we are increasing the paste content also. You got this observation? How this is the base is the 400. Now with the inclusion of chemical admixture, we got the 320. Further replacing cement with the mineral admixture, we got the 106 because efficiency is 75%. If efficiency is 100%, we got to replace 80 by 80 only. Then no, any type of powder content. Hmm. Cement plus mineral admixture plus water. Because mineral admixtures, what why they are replacing mineral and why 75% replacing? Because mineral admixtures will not directly react with the water. That is not hydraulic property. That is not having. How it will work, we'll see in the upcoming slides. What are the equations are there? What happens? We have cement. We added water. Directly, we will get the CSH. Hmm? C2S will react with H2O. C3S will react with H2, and we'll get the CSH and CH, calcium hydroxide, as a byproduct. Whatever the byproducts we are getting CS, that will react with this silica content available from the mineral admixture, because every type, and that silica content plus this CS will convert into additional CSH. So that's why it is giving latter edge strength. Will not, mineral admixtures usually give latter edge strength, and will help to reduce the permeability also because of reducing the pores. Okay, that's why efficiency is less, 75%, because not directly hydraulic properties it is giving. So everybody is able to solve this example, right? And okay, and the concept behind is also understood. So we move forward. So next is pores and porosity in concrete. So porosity we already saw. The maybe aggregate will also porous, and that will also absorb some of the water from the your concrete mix. That's why most of the times it is advisable to use the saturated surface dry conditions aggregate, or in the design mix also we are considering the aggregate water, how much it will be pour. So, and another porosity will present in the hydrated cement paste also. So how we someone has already told, like 18 to 22% by weight of cement water only required to complete the hydration of the cement, but we are already adding most of the water higher side, that is 40 to 55%. So added water is far in excess what is required actually for the hydration cases. So whatever the extra water available, how what will happen with that one? Obviously it will be evaporated, because we will not continuously keep into the curing condition anything. After sometimes we have to even cube also we have to remove, or even slab also will not cure for whole his life, right? So after some time that water will get evaporate. So water will get evaporate. What will happen? That will create or left some empty space in the matrix, concrete matrix, and that empty space acts as a pores. That's why this extra water is dangerous actually. That's why we are increasing the water content. Strength is goes on decreasing because of that extra amount of pores. Understood? So that's why if you see ultra performance concrete, you will see water content is very less, almost zero point 0.2 to 0.23. So you see this one, water plus cement before hydration. If you got some of the in the earlier hydration phase, we got some of the products, hydrated products, water is there and cement content is there, and some pores are there. Then further end of the hydration, suppose we assume all cement has been hydrated, 100% hydration has achieved, no unhydrated cement has been observed, water content is there left because that extra water is there, and some pores. After some times, what will happen? This water will also get evaporate, and this will create total pores. And if we consider some of the unhydrated cement paste is there, so this total pores will be less, because this unhydrated pores cement paste is there out of some of the cement. So pores volume will be less compared to this one. So what indicates the removal of water from concrete over time, primarily through evaporation and related process. It is the fundamental cause of pore formation in concrete. And if it is interconnected pores, that will be responsible for the permeability. We saw in the last first week lecture also. Last question is that pores, interconnected pores and dispersed pores, which will affect the permeability more. So water cement, no, uh, it's not particularly reason. Like if you pour some of the concrete, you will not properly mm, compact also. So that air will be entrapped. Hmm? That will create the honeycombing also. If it is the connected, interconnected, that one, that that depend on the execution process, casting process also. And that's why if water cement ratio is higher and it is available this area then nearby area, and that get evaporated, that after the evaporation that get connected, that will create the permeability issue. Bleeding, actually, bleeding is what will happen. Most of the water will come up above the surface. So that will create the higher water content on the surface. Maybe a surface part will have, after the evaporation, more pores compared to the core. Hmm, hmm, hmm. Okay, because of, yeah, yeah, that may be a capillary pores, smaller pores. Yeah, capillary pores may be available. We'll see how what type of pores there in the lecture, the upcoming slide. Then, if water cement ratio is higher, the pores will also be higher. That is the main thing we observe. Because of the evaporation, pores will create. Okay, see that what type of pores. If we have this is the cement, sorry, concrete. This is the aggregate. We have some amount of unhydrated cement, hydrated cement, chemically bound water within the hydrated cement paste, then gel water, free water, and empty pores. So if you see non-evaporable water, which is non-evaporable water, that is chemically bound water, which is with the hydrated cement paste, hmm, which is chemically bound water within the hydrated products that will not evaporate easily. And evaporable water, which is gel water and free water. So that is that can evaporate and create the more pores with along with the empty pores. So you see, hydrated cement paste generally has capillary pores. Whatever you said, na, that maybe not like exactly capillary, but in the similar range of sizes. Because capillary pores most of the times will observe in the hydrated cement paste. After the CSH formation is there, in that one, whatever the cement that connected pores are there, that will called capillary pores. That's an variation, large variation in size. Then CSH and other hydrates, smaller gel pores which can be evaporated, and spherical air voids because of the not a proper compaction or artificially introducing air that may be greater than 20 micron in size. And porous ITZ, that is already because of the higher water cement ratio, that pores will create in the nearby ITZ. So this is also the size of the pore diameter. You can see gel pores in this range, then 10 nanometer to 10 millimeter, uh, 1 millimeter is range, that capillary pores, then entrain and entrap. Entrap and entrain. We already saw in the air entraining agent. Entrap means unintentionally, right? Because of the not a proper compaction. Entrap, air will incorporate into concrete, and entrain we are purposefully incorporating. Okay. So porosity is, yes. Hmm. Yeah, that's, yeah. Okay. Yeah, I have also saw while preparing this slide. But just for the sizes, actually, one more plot he has given, I think, in the lecture. Okay, okay. I have to see this one then. Maybe we have to ask. Yeah, yeah, sure, sure. In the next lecture, maybe I will see this one sizes. Okay. So in the porosity, what is there exactly? Volume of voids upon total volume. So higher diameter pores, water easy to remove. This is basic concept. The diameter of the pores is will be high, easy to remove the water from that one because less pressure required, right? If it is the diameter is less, more pressure is required to remove the water from that one. So that's why the pores diameter matters more. And to identify the volume of the pores or that purposes, the mercury intrusion porosimetry, one of the major tests is using in the industry or in the labs. If you see in the lecture also, this example has given, we have the different types of pores or different diameter pores, D1, D2, D3, and D4. Okay, and this is the solid matrix. So D1 is greater than D2, greater than D3, greater than D4. If we uh, like force the or pressurize the mercury through this side, suppose, or this side, this higher side diameter. So whatever the pressure required for this one that belongs to the D1 diameter, the mercury will go up to this one. Where mercury in that pressure, mercury will not pour into this one because in this area or in this diameter we require the higher pressure as compared to this one, right? So the volume of D1 will represent that amount of mercury penetration with respect to the D1 diameter. Further, if you increase the pressure, will represent the D2, and the volume of the representing this D2 diameter will represent the volume of pores diameter of D2. Then similarly for D3 and D4. But this is a very idealistic case. But in the real situation, in the concrete, the pores will not exactly like smaller diameter or larger diameter first, then smaller diameter, and then better than smaller diameter. It will the arbitrary place. So this is called as bottleneck effect. What we call bottleneck effect. So this is the limitation of the mercury intrusion porosimetry actually. So suppose D2 is there, we got the pressure that amount where the mercury will pour into the D2 or penetrate, and D3 required higher pressure. Then we got it higher pressure, we get it here. But what happens here? We required less pressure. Similar, there is a difference. Will not have directly pore distribution. Similarly, this one we have the bottleneck effect. This one like real situation. There is an arbitrary placement of the diameter of the pores. So that's why we get the D1, D2 is one of the diameter. Here within this pressure, mercury will penetrate in all the three diameters because this here required higher diameter, sorry, higher pressure, and here required less pressure. So mercury will penetrate all these. It will represent as a one of the diameter D3, which is not actually true because we have the different diameters. Understood? We have the different diameters, but mercury intrusion porosimetry indicating it is one of the D3. This is the limitation of that equipment, but still that is using as a to find out the volume of the pores, and that representing the D4 to D3 pressure 4 to P4 to P3, that is V3 as the volume, V2 representing this is the average diameter volume, this is the average diameter volume V1. Okay, any doubt in that one? In the case you are saying means how much amount of porosity is acceptable like that. Okay, so I am not aware about that one, but I will ask to sir. On next lecture, I will discuss about that one. Yeah, because porosity is directly relation to the strength. So because we are compromising with the strength, increasing the pores. So it is a usual good practice to have the limited or less amount of the pores. But I don't think so. There that will be limit because it's not a direct indicator. We are indirectly measuring the strength only. Mm. Yeah, right. Yeah, yeah. Yeah, we can indicate. Yes, yes, please. Yeah. Hmm. Yeah, actually, I have not observed any particular result, but what I know, as per my understanding, we are getting the volume of particular diameter of pores, and that so we can get the suppose D1 diameter is there, D1 diameter pores, how much amount is there? That volume will get it. But hmm, hmm, hmm. Yeah, it may be. Hmm. Okay, I will get back to you this one because I will see how much like how result will be display and how it is interconnecting with its results with the diameter and volume. Okay. Yeah, yeah, sure, sure. Next lecture I will discuss about this one. Yeah, okay. So further, there are different types of admixtures available, chemical and mineral. So as you see, everyone know about the superplasticizer. Most of the civil engineers know about the superplasticizer, which will be easily used in the labs or in the construction site. Then accelerators in the cold countries wherever we require the hydration fast, or in the water concreting we require the hydration fast. So we are using the accelerators also, or the different types of chemical admixtures such as set regulators in the accelerators, retarders, water reducers, and high range water reducers. These are the superplasticizers, air entrainers, air entraining agent, and corrosion inhibitors. So corrosion inhibitors to avoid the corrosion of the bar in the concrete. We'll put it to that as an admixture into the concrete. So in the mineral admixtures, most of the mineral admixtures are the industrial byproducts. So main motivation behind that is utilization of industrial byproducts because that's having the certain amount of environmental concerns for depositing somewhere and that all things leaching effect. Then to increase or to reduce the cement consumption by replacing the cement we are using as a mineral admixture. So we reduce the cement consumption, which will be helpful for the reducing the CO2 consumption of the or CO2 emission of the cement industry, leading to economic benefits as the cement is a very highly cost material. Then reduction in heat of hydration because most of the I already discussed about that one. Like most of the mineral admixtures give the latter age strength because it is directly reacting with the CH, which is the byproduct of the major component, binder component as a cement. Then improvement in durability of concrete because it reduces the pores in the latter age hydration and achievement of higher strength requirement because of reducing the pores. Pores reduces ultimately strength also increases. If you see this table, water cement ratio, Ca indicates chemical admixture, slump, strength, and comment. So if you see water content is 180, cement is 360, water cement ratio 0.5, and we are not using any type of chemical admixture. Slump we are getting 8 centimeter and strength we are getting 32. This is the base mix. What we do, we reduces the water content 160 and we same cement content is there. So what happens? We reduces the ultimately water to cement ratio. So we saw water cement ratio has the strength relations. So we got reduces the water cement ratio, me increases the strength. But and we are using this water we have reduced because of the chemical admixture we have used. Which one? Maybe water reducers or high range water reducers as a superplasticizer. So if we increase the strength, why? Slump has not changed, or it may be changed. Hmm? Yeah, already water has changed. See, 180 to 160 we had. Yeah, but because of chemical admixtures, we are not changing any slump value. We are getting the same slump value for that one. But we reducing the water cement ratio. That's why we are increasing the strength. Now see third one. We 160 is the water content. Cement content we reduces 320. So we kept the water cement ratio same. We has the chemical admixture. So slump will be same because of the chemical admixture and water content. And strength, although we are reducing the cement content, water cement ratio is same for first and third one. So that's why we are getting the same strength because water cement ratio affects the strength. So two main properties. What is that one? Because of the inclusion of the coarse aggregate, maybe we can reduce the water cement ratio and increase the strength, and we can reducing the cement content. So we reduce the cement content, cement saving. So two benefits are there. One is the higher strength we can achieve by reducing the water cement ratio, and we can achieve the economical mix by reducing the cement content. Another is that we kept same 180, 360 cement, zero point 0.5 water cement ratio. Still we added chemical admixture. What happens now? Flow will be more. That is slump will be greater than 8. Although strength is same because of the water cement ratio. So this is called as plasticizing action. Under, yeah. Three. Hmm. But yeah, but majorly two are more useful for us. One is higher strength and cement saving. Plasticizing action is a like a conditional basis. If you require plasticizing action, then only you can use it for that purposes. But yeah, so that is only giving the plasticizing action. It is not like flowable concrete, but it will be more workable than the earlier one. So that's why that is called as a plasticizing action. But whatever the benefits we have with the chemical admixture, that water reducing admixtures, higher strength and cement saving, both are giving. This is the structurally more durable, structural aspect is more or useful, or cement saving is economically more useful. So these two aspects we have to understand, right? Okay. So how we'll understand the dosage of mineral admixtures? We saw in the previously one example, that is efficiency of the mineral admixtures, because it's not a directly the hydraulic action will give. So that's why efficiency of the mineral admixture is more important. And the desired result. Suppose we are replacing the cement with the fly ash and we require to get the 80 MPa or 50 MPa strength, but we are not getting the desired strength. So we have to make the changes or adjustment into the concrete mix accordingly. So dosage of mineral admixtures depend on the two. One is the efficiency and the desired result. General range, slag has 30 to 70% by weight of cement by replacing, fly ash 10 to 30% by weight of cement replacing, then silica fume 5 to 15% by weight of cement. And addition, if you see uh, fly ash, most of the research papers also you will find out the high volume fly ash. Almost they are using 60 to 70% also. But code has not recommended beyond this one till the date. Maybe in the future amendments it will go beyond that one also. But at this moment we have these values only. But research is going on up to 60%, 70% high volume fly ash also. So whatever the reactions I told, that is C3S plus H2O in the cement as a binder, main binder, CSH plus calcium hydroxide will get it. Here C2H plus H2O, CSH plus calcium hydroxide. And that calcium hydroxide react with silica content available in the mineral admixtures. different types of mineral admixtures, and then it will create the additional CSH gel. So ultimately, the matrix which having the concrete matrix which having the mineral admixture which will be richer in CSH phases and poorer in the amount of CH, because most of the CH will be consumed by this silica and create the CSH gel. So this is the basic chemical reactions occur into the mineral admixture based mixes. So further, as we see, mineral admixture inclusion, we saw one example which has the higher amount of the paste content, right? We got the extra amount of paste content because of the 106, in place of 80 kg cement, we got 106 kg of mineral admixtures. So that's why we are getting the higher amount of paste. If you see normal concrete and self compacting concrete, see normal concrete has cement 10%, water 18%, this is air is 2%, fine aggregate 25%, coarse aggregate 45%. But in the case of self-compacting concrete, where required the particular type of compaction with the self-compaction with the concrete itself, so we require to use mineral admixture as a, anyone knows what we will use in mineral admixture in self-compacting concrete? Mainly use silica fume and fly ash. So you see 10%, 18% cement and water, 2% air is there, but this 8% will be the what we call that's mineral admixture. So extra cement paste or sorry extra paste content will be available in the self compacting concrete. And here you see fine aggregate is almost similar, but coarse aggregate content has been reduced to get the proper compaction and flowability for that particular mix, because SCC has a more flowability than the normal concrete, right? Because it has to flow through the rebars itself. So that's why coarse aggregate, higher size of aggregates got reduced in this condition. So understood that mineral admixtures increases the paste content and their dosage requires depends on their efficiency and desired result and this chemical reactions. So mainly mineral admixtures gives latter age strength. Okay, fine. Yeah. So we'll see some of the examples. Then you'll get some idea to how to solve the week 2 assignments. We'll quickly go through all the questions. So two concrete mixes are there, A and B. Mix A is normal concrete without admixture, and mix B use water reducing admixture. Cement content is same in both the mixes. Workability of the mixes measure using the slump test, and it was found to be the same for both the mixes. So what will be the answer? Which concrete will have the highest characteristic strength? Anyone? Mix A is higher. Second option someone told, that is having mix B is higher than required A, right? Yeah. Why? Because we, although we kept the same cement content, we are getting the same slump value, but we are using water reducing, means we already reduced the water content. So water content reduced in the mix B indicates higher strength. So that's why second option. So similarly, example, you see concrete A has without admixture, concrete B with water reducing admixture, equal cement content, equal slump value. Suppose here water cement ratio is 0.5. So we are using water reducing admixture. That's why here water cement ratio may be 0.35. So that's why strength will be concrete B become higher because of the direct relation between the water cement ratio and strength. Okay. This graph also indicates that one also. We already saw that one. Okay. So next one is that in the context of slag, addition to the ordinary Portland cement. Statement 1 indicates slag addition reduces its air content. Statement 2 says slag addition increases its water demand. So what will be the answer? Hmm. Okay. Okay. So someone okay. One is giving answer one and one is giving answer two, right? Any other? One is right and two is false. Oh, right. Slag addition why reduces air content? Because slag particles are generally smooth and denser particles, so which will increase the packing density and which tends to reduce the entrap air through the concrete matrix. That's why it will reduce the air content. And in the case of slag addition increases water demand, that is wrong. Why? Slag usually has a lower or similar water demand compared to the OPC due to its smooth, glassy surface and lower early activity because it gives the latter reaction because once CSH is there, then it will get react. So it will not increase the water demand in the initial phase. Okay. Next, silica fume addition increases its lateral strength and decreases its permeability. Statement 2. Silica fume addition decreases its mortar bar expansions due to sulfate attack but increases its permeability. Out of this, okay, who is wrong? Anyone? Any other answer? Hmm. First one is correct, right? Yeah, right. First one is correct. Second one is wrong. Why? See, silica fume is highly pozzolanic and very fine, leading to denser microstructure. And we already saw it's giving the lateral strength and significantly reduce the permeability because lateral strength reduces the void by creating the extra CSH. That extra CSH reduces the voids, and because of the reducing the voids, we are getting the lateral strength. So that's why it decreases the permeability because no voids, no permeability. Second one, silica fume helps to reduce the expansions by refining pore structure and improving sulfate resistance because pores will not there, then sulfate will not penetrate through the concrete and will not able to give any sulfate attack over the concrete. So it will give sulfate resistance and it does not increase permeability. Instead, it decreases the permeability. That's why statement 2 is wrong because here it indicates increases permeability. Only statement 1 is correct. It gives lateral strength and decreases permeability. This is the scanning electron microscopic image of silica fume. You see, the particle size are almost like circular. Next, the accelerators are sometimes used during colder environments to increase both the setting time and the heat of hydration. And statement 2 says the dosage of chemical admixtures is usually greater than 4% by weight of cement use. So, which will be the correct one? One is true, second is false. Any other? Okay. Hmm. Hmm. Okay. Correct. Both, yeah, both the statements are false because accelerators are used to reduce the setting time, not increase the setting time, right? And the second one, what says up to 4%? It, it is not up to 4%. It is up to 2%, less than 2% mainly used percentage of the weight of the cement. So both the statements are false. Next, so if you have to do some of the calculations here, you see what question indicates they have given some of the constituents mix 1 control, mix 2 and mix 3. So mix these are the constituents and what they said some information they have given. Mix 1 does not contain any industrial byproduct. IBP indicate industrial byproduct and serves as the control mix. Okay. So and mix 2 the industrial byproduct is added to replace only 60% of the fine aggregate. So 60% of the fine aggregate replaced with the industrial byproduct. Mix 3 industrial byproduct replaces 20% of the cement also in addition to replacing the 60% of the fine aggregate. Already 60% fine aggregate replaces, then additional 20% of cement also replaced by industrial byproduct. And given some like specific gravities of cement 3.1, fine aggregate 2.6, coarse aggregate 2.7 and IBP industrial byproduct is 2.9. So can anyone please tell me what will be the value of X in the mix 1? That is the first question. What is the value of X in mix 1? We have water, cement, all are in kilogram per meter cube. These things. We saw so many examples in the earlier recap, so you get some idea over from that one and try to solve this one. Anyone? Okay. See, in the mix one, we consider kilogram per meter cube means whole mix is in 1 kilogram per meter cube, right? One, yeah, 1 meter cube whole mix is 1 meter cube. So total volume will be 1 meter cube. So we want to calculate the X. So one is the addition is one. So we subtract all the volumes of the mixes from the one, and we require the coarse aggregate. Coarse aggregate we have specific gravity 2.7. Hmm? So if you see one minus water is 200 by 1000 minus 400 by 310 density we divided by density to get the volume minus 700 by 260 for the sand and whatever the value we are getting here we multiply by 2.7, that is specific gravity into 1000, that is density we are getting. So we'll get it 1085 kg per meter cube as a coarse aggregate content. You got it how we have calculated all the mix we all the mixes we are getting in kilogram per meter cube. So 1 meter cube means we have to get the volume of that one and we have to reduce all the or subtract all the volumes from the 1 meter cube. So we'll get the X, that is coarse aggregate remaining volume, and we multiply with the density we'll get the 1085 kilogram per meter cube, and the answer is given in range 1080 to 1090. Next is what is the value of y1 in mix 2 and y2 in mix 2, that is next question 7. So what is the basic information we have given first? In mix 2 industrial byproduct is added to replace only 60% of the fine aggregate. So sand is 700, right? So out of that one 60% has been replaced by industrial byproduct. So how much is remain? 40%, right? 60% has been replaced, so remain 40%. So 700 into 40%, how much it is? 280, right? So y1 will be the 280. What y2 indicates? How much will come now y2? IBP replace 60% of sand volume basis, right? So Y2 will be zero point 0.6 into 700. Zero point 0.4 is there, 60%. IBP is 60%. So 6.6 into 700 into 2.9, the specific gravity of fine aggregate and coarse aggregate. Oh, sorry, yes, IBP. So we got the value of 469. We got the value that is 40% remaining, 60% replace. At 60% we got out of 700, and then multiply and divide by the space, each other specific gravities. So we got the value of 469. Understood? Yes. So in the mix 3, so mix 3, what they ask Z1, Z2, and Z3. And what information they have given? The mix 3 IBP replaces 20% of the cement also, in addition to the replacing 60% of fine aggregate. Already we are replacing 60% of fine aggregate. So maybe then Y1 will be the Z2 same, because only 40% sand is remaining. Here also, we are replacing 60% of sand, and here also replacing 60% of sand. So Z2 and Y1 will be similar, right? Understood? Because what is said in mix 2, IBP is added to replace 60% of the fine aggregate. So out of 700, we are replacing 60%, remaining 40% Y1. And Z2 also says that condition is the same in mix 3. So Z2 and Y1 will be the same. But additionally, what it says, 20% of the cement also replaces. So 20% cement of the replaces. So out of 400, 20% gone, remaining 80%, right? So 80% of 400, how much? 320. So Z1 and Z2 we got it. Z1 320, right? And Z2 280, because Y1 and Z2 similar. Now Z3, how much will be the Z3? 60% from the sand we have replaced, and 20% from the Z1 we have replaced. 20% from the cement and 60% from the sand. So we have to add both, right? See, 60% of sand, that is 469, 20% of cement. So volume, 20% of cement, how much? 80. 80 by 3.1, 25.8. So mass of IBP, how much? 25.8 into 2.9, 75 kilogram per meter cube. So 75 plus 469. Then we'll get this one, because we got the two replacements. So I have two replacement, we have to do the addition. Then we'll only we get the Z3 value. That is 544 kg per meter cube. Understood? Basically, we have to get with the whole volume basis only. 1 meter cube, then we can calculate the for the control one, and then with the replacement, we have to play with the specific gravities. With the help of the specific gravity, we can easily calculate this one. Once I will upload this PPT also, you can go through once again. You can solve on your own. You will easily identify. Even in the lecture also, sir has been solved this one. Okay. Okay. Only last four questions are remaining. So slump is primarily determined by unit water content, and strength is primarily determined by the water cement ratio. Simple, very simple. We both right, because in the beginning itself we are seeing that thing only. These two graphs. Slump is dependent on the unit water content, and strength is dependent on water cement ratio. Next, aggregate properties affect the slope of unit water content versus slump curve. For bigger coarse aggregates, the mortar requirement is higher than smaller coarse aggregates. Tell me what will be the answer? Hmm. Hmm. Second is false. right? Because already we saw graph has the aggregate shape, size affects the slope of unit water content versus slump curve. That's why three lines I have shown that one, right? And for the bigger coarse aggregates, if the size of the coarse aggregate increases, the specific surface area decreases. That's why mortar requirement is less, not higher. Here it's given opposite. That's why it is wrong. Okay. Next, if the slump concrete needs to be increased, the sand to aggregate ratio needs to be increased. Second, if the air content needs to be increased, the unit water content needs to be reduced. What will be the answer? One is right. Second, okay. Any other? Second is true. Okay. First, okay. Statement statement one is false. See how we'll see. If the slump of concrete needs to be increased, the sand to aggregate ratio needs to be increased. This is the sentence. But what happens? Increasing the sand content means higher S by A ratio is there. Sand is higher, aggregate content is low. Improves the cohesiveness of the mix and enhances the workability. As I said, lubrication increases due to the increasing the thickness surrounding the aggregate, which helps increasing the slump, reducing bleeding and segregation. But this happens up to the optimum sand to aggregate ratio. Not it's not a generally valid sentence because slump of the concrete mainly depends upon the unit water content, not directly dependent on the S by A ratio. Because S by A is here aggregate shape, size, texture will be different, right? Hmm. The second one is air content needs to be increased, the unit water content needs to be reduced. Air in concrete is primarily increased by using air entraining admixtures, not by reducing water content. So, in fact, reducing water content generally reduces workability and does not directly increase air content. Okay. Mm. Yeah, similar slump actually workability increases, but it's not direct relation we have. It's not valid in the all the cases. Similar to this one also, optimum is it is optimum condition we can get it for that one. So that's why both the you said slump is dependent on the unit water content and the strength is dependent on the water symmetry. So these are the universally valid conditions. So 14.1 in the context of bleeding in fresh concrete, a water reducing agent can also be used to reduce the unit cement content in the concrete mix. And pozzolanic materials used as a mineral admixtures have hydraulic properties similar to the cement. Two is false. Okay. First, okay, right. One is true, two is false. Because we saw water reducing agent has two advantage. One is reducing cement content and another one is reducing or increasing strength. And pozzolanic materials used as mineral admixtures does not have hydraulic properties actually because that's why it is dependent on the CH content from the matrix. Okay, these are the explanation for that one. So thank you. If you have any other doubt, please let me know so I can cover in that next session. What? Last slide. Huh? I'm not getting you. You are asking about the question, right? Submission date. Yeah, 4th February. Yeah. Okay. So that result of the mercury intrusion porosimetry I will discuss in the next lecture. Okay. 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 Thank you then. Yeah. 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 Millimeters. That one also I will discuss. Yeah. Okay. Yeah. Thank you. Yeah. Bye. 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 Good night. Good night. Thank you. Good night.